Okay, so really quick discussion of induced EM fields on human health. The frequency of transmitted and home use power is around 60 hertz. This is considered to be extremely low frequency. Okay, so photons emitted by extremely low frequency radiation are not energetic enough to ionize living cells. They can't harm cells in the same way alpha, beta, and gamma rays can. The alternating field, however, can set up small alternating currents in the body. The body has a lot of polar molecules, a lot of water, and these can cause the molecular structures inside of your cells to be altered in response to Faraday's law, because of Faraday's law. So the effects of non-ionizing radiation, like radio frequencies and different things on biological tissues, is an ongoing area of research. So just so you know, there are many studies that have shown that ELF fields do not harm genetic material, but they still seem to affect living cells, or at least the research isn't totally conclusive. There have been articles or studies done on how power lines, high transmission lines, high voltage power lines have been linked to childhood leukemia and other forms of cancer, and it could be because of the eddy currents produced in your body. So another obvious health risk is the danger of electrocution. So the effects of the radio frequencies from cell phones could also cause cancer as well. You'll have an extra credit opportunity this cycle with This American Life podcast, and so you should listen to the podcast. I'll have it posted, take notes on your own, and you'll answer a question during the Topic 10, Topic 11 exam. AC versus DC. So when electricity became available for distribution to households, two main arguments in the United States were put forward. One was put forward Edison. Edison thought that it would be practical to use DC power stations, having large wires coming from the power station directly to people's homes, and the counter argument was put forward by Tesla, who sold his ideas to Westinghouse, and that was the alternating current supply. So the power transmission today, obviously Tesla, Westinghouse went out. It is alternating current. And given that AC can be stepped up and down by transformers and DC can't, we can see why alternating current is preferable to DC for transmission. It's easier to produce alternating current in large quantity as well, due to the rotational nature of turbines and things like that. So, however, most of the electronic devices we use today require DC, direct current. Thus, there needs to be a way to convert between alternating to direct current, and we will see that coming up. What if, though, we need to power some devices that require direct current, and we want to power them using an alternating current supply? Well, we can take advantage of a device known as a diode. A diode is a semiconductor that only allows current to flow one way. It's the symbol here shows the direction that it allows current to flow through. An LED, just so you know, is just this particular type of diode. It looks like this glass piece on top. An LED is a light emitting diode, has a longer end. The positive end is the longer terminal and must be connected to the positive voltage supply. This side is the negative voltage supply, the shorter one. And if it's not connected correctly, it doesn't illuminate. So on the schematic, you connect positive here and negative there. So it shows you the direction that current needs to flow through. Thus, if we supply an AC input to the diode, only the positive lobes of the alternating input will be allowed to pass. So only when the voltage is positive will the diode allow the circuit to be closed. Is the circuit closed? Conversion of AC to DC is called rectification. So this particular example where we have an AC source connected to a diode is called half-wave rectification, because quite literally only half of the voltage is transmitted. We've lost essentially half of the energy. If we're clever, however, we don't lose any of the energy. If we construct a full wave bridge rectifier with 4 diodes and a resistor, we can harness all of the power and convert it from AC to DC. So I have this AC power supply. You need to draw this because yes, IB expects you to understand how the diode bridge rectifier works. We have an AC power supply. We have our 4 diodes. Please note the direction of these diodes. We have a resistor. This resistor exists to reduce the voltage, to drop the voltage for our DC output, and this here is the DC output. It's interesting because in this way we don't lose any of the negative lobes. We're able to convert all of the energy, even when the current is reversed, we're able to convert all of that to a monodirectional current. All right, so let's see how the bridge works. At the instant shown, let's say that the left terminal of the power supply is positive and the right terminal is negative. So this is the way the current flows. At this junction, it's only permitted to pass through this LED. At this junction, or this diode, it's not necessarily an LED. So at this junction, it splits. It either goes to the output, as an output is the DC output, which is positive, or it travels through the resistor. Now, because there's also a negative end, we have where the current flows through as well. So the current travels here, grab my black, up, chooses the correct path, the only path that it can take at this junction through here. Part of it is split to the output, positive output. The rest of it goes through the resistor, where it has effectively been split in a sense. Part of it goes through the LED, connecting to the AC power supply to complete the circuit, and the other part of it goes through to the negative output. So let's see what happens. And so you'll notice that at any point in time, only 2 of the diodes are utilized in the bridge. Now, what happens when we reverse? We make the positive on the right and the negative on the left. The exact opposite. So let's follow from positive to negative as is conventional with our DC circuit. So the current goes through here, it goes up, it splits at this junction, only able to go with the flow, comes out again up top as positive, current has split then through the resistor, splits again to the negative output, or following the path that it can take, comes back to the AC supply. So this is the rectifier. It's really interesting that with this setup, no matter how the AC current is oscillating, the DC has the same output. This is key to utilizing electronics with alternating current. So the diode bridge rectifier isn't perfect in of itself, because essentially all it's done is converted negative lobes to positive lobes, but there's still separation between those lobes. The voltage isn't constant. It varies between 0 and its maximum output twice each period. That difference, that fluctuation is much too large to make electronic devices usable. So by adding a capacitor in parallel with the resistor, you're able to smoothen out these waveforms as such. There's less of a dramatic drop between the voltages. And then in that way are you able to run electronic devices. And this is the schematic for a capacitor.